We're going to talk about a 9340 relay. We're going to teach you how to use this in other applications. We're going to show you how to wire it up to a blower motor running low speed and high speed. We're talking about on the smart board on how to wire this thing up. Very simple. This is a very good relay. We want to make sure that this is a stock choice item. We want you to look at it very simply and just hope that you feel more confident with it. So it's on your truck. I think it'll get you out of a jam. Stay tuned. Today we're at the CANTEX Box and we're going to talk about the 9340 relay and all the terminals that it has here. I have a light here. It's not a magical light, but it does require L1 and L2 to be present up here between T1 and T2 for this to come on. We have a live voltage here. This puts us danger close and allows us to be able to train and deal with the same terminal names and power supply that's out in the field, and allows us to be able to strip away the rest of the equipment so we're not looking at everything else that is irrelevant to understanding the 9340. So we're focused on one load and we're focused on a 9340 relay. Now we can talk more about the relay without any distractions. A little bit about the CANTEX box. We have transformers and contactors in there that the moment we supply power to it, this light bulb will come on. I'm going to go ahead and show you here between L1 and L2 that we have 240 volts. Let me just get a check to make sure that's visible. I'm going to go ahead and put the backlight on. Hopefully this helps out. All right, so that's a Roger. L1 and L2 are good to go, showing us 241 volts. Obviously, there's nothing between T1 and T2 because we haven't applied power yet. I have 24 volts between R and C here. I'm going to move my arm out of the way. You can see that's 27.8 volts. And with that, we can go ahead and introduce L1 and L2 up here so we can see that if I remove any one of those combinations, L1 or L2, our load turns off. Now, in our real world, we're only breaking one leg of power. That's why it's important to show you how to get this load to come on without a light bulb. This load can represent a fan motor that's 240. It can represent a compressor that's 240. A set of heat strips, it doesn't matter. And so this is pretty neat to be able to show how to break a leg of power when we're using something as simple as a light bulb here. I'm going to use black and yellow between L1 and T1. And the moment I touch this, you'll hear a click because there's a contactor in the box. But this is going to put that other leg of power that's sitting up here, and the load's going to come on. I'm going to turn that off real quick. I'm going to come down here. I want to show you that because we wired L2 to T2 without the relay, and we don't have L1 to T1 up there, there's no load on. But that doesn't mean that there's no power present, because if I went between, I'm going to put my light back on here, if I went between L1 to L2, you're going to read the difference of power of 241 volts, 242 volts. Now if I kept one lead here and I went it up to T1, you notice I still have 240 volts. And if I went over here to T2, I have 243 volts. That's because L2 is present all the way through the load. And so it's very important when we're running power through relays. I'm going to show you how we can still see what we just saw here on this relay. We can go across a couple of points and read 240 volts. So we're going to get into it, and I'm going to take L1, I'm going to wire it up to the first terminal on the top left-hand side of the relay. It's called terminal 1 there. That's going to be a line voltage terminal. On this top portion of the relay, this is one pole. The second portion of the relay would be terminals 4, which is line voltage. And then I have a switch on 5 and a switch on 6. Well, that's an independent pole all by itself. So that makes those two poles, but because it's doing two different jobs, it's throwing in two different directions. So it's a double pole, double throw. It takes 24 volts to switch it. So with that being said, terminal 2 has L1 present on it. So I'm going to put my backlight back on my meter, and as you can see, I don't have any voltage, or I'm sorry, any wires landed on terminal 2 here. But if I put my lead on terminal 2 and I came back over here to L2, you'll read that I have 242 volts. But if I came over here and I put a lead on terminal 2 and a lead up here on 1, I read 0. I'll demonstrate it down here as well. L1 to 2, 0. 2 to L2, there's 240. Back to L1, there's 0. That's because L1 is present all the way through to the normally closed portion of the relay. Now, there's no power here on 5 or 4 until I give it power. So I'm going to come over here and I'm just going to shift this down to terminal 4, which is the second pole on this relay. And I'm going to have the exact same thing. I'll put one lead on L2. I'll put my other lead on terminal number 5, which is normally closed from 4. And as you can see here, I have 240 volts of power. I'm going to go ahead and leave it on that pole for a second here. And I'm going to show you that if I were to come out of terminal 5 up to terminal 1, the light will come on because we'll be providing it the second leg of power that it needs. So we're going to go ahead and wire it up to T1, and the light came on. And so I didn't need 24 volts to make that happen. The same thing, if I'd come up and I'd take power away from it and I put line voltage up here to terminal 1 on the relay, 2 is sitting there with this voltage present. All I have to do is connect my T1 terminal up to 2 and my light comes on. So this relay is pretty cool because I can get loads to energize without 24 volts. I'm going to show you what happens if I leave it like that and apply 24 volts. We're going to go ahead and use green, and we'll just say that this is common for now. I'm going to run it up to common, and then I'm going to take red, and I'm going to wire it to the other side of my relay, and you're going to see the load come off. And so now that I've applied 24 volts to my relay, I break power between 1 and 2, right? And so if I were to simply remove any one of these off the coil side, then the normally closed portion of the relay is now energized. Unenergized, energized. So typically when you're wiring these relays up, you're going to use 1 and 3. Like if I were to run this to a fan motor, 1 and 3 may be all the terminals that I need. So if I get a G call, the load comes on. If I lose a G call, the load shuts off. So I'm going to go ahead and do the same thing. I'm going to run this down to terminal 6, which is on the second pole. That second pole has no power on terminal 4, which is the line voltage terminal. So I'm going to have to put line voltage on 4, and the load will come back on. And it's simple as that. I'll move the 24 volts off of it. And as you can see, that second pole is doing the same thing that that top pole is doing. When I come off of 6 and I come over to 5, there's no power on terminal 5 from 4 because we have 24 volts on the relay. If we remove 24 volts on a relay, the light comes back on. This is pretty much everything that this relay can do. Now, I wanted to show you where power is present, okay, when there is. So I'm going to come back up here in the very traditional manner you would typically wire this. I'm going to come up to 3, and the moment I put line voltage on terminal 1, the light will come on. Okay, and now if I were to take 24 volts off of my relay and I wanted to see, is my relay open or closed? Say I can't get down here to see if there's 24 volts present. We know by what we're doing there's no 24 volts present because we just removed it, right? But let's just say we wanted to find out just by using our meter, because your meter is a tool. It tells you when things are open, when things are closed, when there's power present. Ohms is measuring resistance, is measuring a lot of things. We're reading microfarads with it, DC and AC. All this stuff is very important. So you need to know how to read your meter. So I'm going to go between terminal 1 and terminal 3. And as I showed you in the beginning of this, you'll see that L2 is present to T1. I'm sorry, L2 is present to T2. Through the load is present on T1, which means it's present right there on terminal 3. So between 1 and 3, we should read the same voltage as we read between L1 and L2. So we have 241 volts here. And if we come up here, you should read the same power supply. 200 and, let me get a good contact on it. There we go. My light just went off. I'm gonna turn that light back on there. It'd be nice if these lights stayed on until you turn them off. 241 volts. The moment we apply 24 volts, L1 will come across to 3, which will force the load on. And you're now going to realize that we read 0 volts, even though we know there's power there. There's L1 present on both sides. And because we can't read a difference of anything like we could if we did this, okay, or this, or this, because we don't read anything here, that means it's the same leg of power. Doesn't mean that 0 means no voltage. So I'm now going to undo these, and I want to show you contact voltage, and I want to show you coil voltage utilizing your meter, because sometimes the diagram's not available, even though that they give you a nice diagram on the very face of this relay. It's very hard to not understand normally closed and normally open, look at the face of this relay and not understand what that means. So I'm going to go ahead and just remove all the power off this relay, since we're done talking about the power portion. Go ahead and remove L2, T2. I'm going to go ahead and turn the power off for safety. And I'm going to show you here with my meter, if I went to continuity, my 9-volt battery on the meter, once it reaches contact here, it's going to ring out. It's a little ringtone. And so if I wanted to see where's my contact voltage, you'll notice that if I went here, it's going to kind of be all over the place. It's going to read a resistance. You got 19, 20, 24. It's kind of jumping around, right? Well, if I come up here, you're not going to see any numbers. So I'm going to come up here between 1 and 2, and you're just going to read 0. And so I'm not measuring any resistance there. I'm getting a ringtone, but I'm not measuring any resistance there. Same thing between 4 and 5. I'm not measuring any resistance there, right? So I'm just getting a ringtone, right? If I came across these, you're going to read absolutely nothing. Let me put that back on. I'm going to go 4 to 6. I read nothing because it's open. So I know 4 and 5 are closed. 4 and 6 are open. Same pole. 1 and 2 are closed. There's no resistance there. 1 and 3 are open. And if I wanted to go and read across my coil, I'll get a ringtone. And I'm going to get resistance there. I'm showing 19.3, 19.4. And that's a difference there of reading resistance and not reading resistance. Now some meters, they don't have a ringtone. Some of them do. It doesn't matter. If you're reading, you're looking for the numbers. So if you're not seeing numbers there, then it's contact side. If you're seeing numbers there, then it's coil side. Make sure you're on the right voltage so your coil doesn't say 24 volts and your coil voltage that you have on your unit is 208, because that would not be good. That's going to create a lot of work, create a lot of problems, and somebody's probably going to have to come over there to help you out if you made that mistake. Most likely, you're probably going to be reminded of it. So try not to do that. Take your time. Don't play with power. Play with the meter. Stay tuned. We're going to take it over to a motor where I've got a couple of light bulbs and I've got a couple of speeds wired up on a motor. And I'm going to show you the same thing over there, utilizing all these terminals. All right, so we got our PSC motor here. We have 3 speeds, low, medium, and high. As you can see, I've added a light bulb up here. One's red, one's blue. And I already pre-wired these to our 9340 relay. And so I also took the liberty of taking 2 speed taps, red and black, low and high speed, and I have those wired. So I have the red wire coming up to terminal number 2, and then on terminal number 3 I have a light bulb coming over, running off of that, and then I have terminal number 6, I have my high speed motor winding wired to that, and then I have my other light bulb wired to that. Now I had to kind of do a little bit of crisscross there, because what I'm trying to do with this is show you that by wiring every terminal present, how I can take a double pole, double throw, and get all the job that I can get out of it in a simple video. And so the motor needs 240 volts. The light bulbs need 120. So the other side of my light bulb is present here. This is my neutral, so I got to create a path. So with that, I have an extension cord that I'm going to use for neutral. Also, I wanted to show you with my power supply, which is off screen, but if you can look at my meter here, hopefully that light doesn't affect you and we can read power. Right now, I have to turn it on. You should see 240 volts of electricity. Does that show up pretty good? So we have 240 volts of electricity, and I'm going to come a little bit further down so you can see that we have low voltage present too, 27 volts. And with that power supply that I have here, I'm going to go ahead and use that 240 to wire my motor, which is missing both legs of power right now. So it's pre-wired. I need to land line voltage, one leg of power up to my relay, and the other leg of power, I need to wire it to the other side of my line voltage for my motor, so I have both legs present. Now, there also has to be 24 volts present on the relay. With that, I can run the relay when there's not 24 volts present and when there is 24 volts present, the moment I put a leg of power there. My lights are going to need a neutral because there's no neutral present in the 240 application, so I'm using an extension cord. I'm just going to plug my wire in here. This isn't safe, so I don't recommend you doing this at home. But for the purpose of this video, we have to show you where we're getting our power so we can be transparent. We have a neutral now. And so I'm going to come around on the other side. So we're going to go ahead and take our line voltage. We're going to put it up on terminal 1. And because I have 2 poles that need that same leg, I'm going to come off of terminal 1. And I'm going to go ahead and energize terminal number 4, which would be the second pole. Now, we have a light that came on, but that doesn't mean that the motor is going to run yet because I have to have 240 on my motor itself. I'm going to replace this alligator clip because it's not so fancy right now. That way we can get a better connection. So we're going to come to the second pole, which is terminal 4. And I'm going to run it up to my top pole on terminal 1. Here we go. And so we have one light that's coming on because of neutral, okay? And I'll go ahead and unplug the neutral here. When I unplug the neutral, I stop the path. So I'm going to come back over, I'm going to plug that neutral back in. So we have a path of electricity for the light. Okay, And so now we have a path on the light. As far as the motor goes, we're missing a full leg of power. We need to put the second leg of power there. And once I do this, you'll see that that speed, which is wired up here, the red wire is wired to the normally closed. That is low speed. So low speed's going to run. And so maybe I want to use this application to say, hey, I got a red light. That means the fan is running in low speed, right? And so what happens if we were to apply 24 volts for the fan to run in high speed? Well, the moment we connect 24 volts to the relay, we'll see everything switch. Because right now we're doing two jobs. The speed kicks up on high. It dropped out low speed. The light bulb for low speed turned off, and the light bulb for high speed turned on. And this is an example of using both poles doing four different things. We have low speed, high speed, and two different light bulbs to indicate what speed that they're on. And say maybe these light bulbs had a larger circuit ran across the building, and I just wanted to utilize this relay so I knew as an indicator something was happening. You know, maybe a machine as an indicator that, hey, there's a machine on. What mode? Oh, it's high speed mode. Okay, now it's low speed mode. Okay, so it doesn't matter the application. The point was to demonstrate a 9340, make it busy, put a lot of stuff on it, and help you better understand that you know, we can do more things utilizing this relay than just, you know, hook up one speed on a fan motor. So here I'm running two speeds, low and high speed, and two different indicator lights to tell me, you know, what I've got going on. And again, you know, this neutral is the reason why my lights are coming on. So if I were to take neutral out, you know, we'll lose our path. So we're using this relay to take a leg of power, run it through one load and back to neutral, take a leg of power, run it through a second load, and with the other leg of power, having a full 240 volts to energize a 240 volt load. All right, so we're going to put this up on the smart board, and we're not going to have all this on the smart board. We're going to talk about the relay itself on the smart board, the timelines and all that, so stay tuned. All right, this series of videos is introducing many different relays. We've talked about the timeline on these other videos. I'm going to continue to talk about this timeline. I want to make sure that you understand where we've evolved from, because sometimes you have to go right back to it. And so it's good for you to know your history. It's good for you to understand what makes these motors come on and run, because it has been integrated several times with manufacturers with different components. As you can see here, if we go back, you know, a solid 30 years, we had three components, and if you look at where we're at today, we're at one component. So everybody's familiar with ECMs by now, if you've been in the trade, because they came out back in the, you know, second decade in the 2000s. ECM stands for electronically communicating motor, and PSC stands for permanent split capacitor. That's why you see capacitors here. When we get to the ECM, that one component's gone. So inside that module, they already have those capacitors there for you. And they started to integrate the relays inside the motors as well. So now these modules pretty much are a one-stop shop. So you have all these additional components built inside of it. So if it fails, all you can do is replace that one part. That's not a bad thing. If the customer's under warranty, you know, get them up and going with the, you know, module or motor, whichever component it needs. But you also want to look at what caused that to fail, because you don't want to repeat that process every 6 months or a year where you're constantly replacing motors because motors are failing due to high static pressures, or motors are failing because things just aren't wired properly. If you have to replace this motor and get your customer back up and running, it helps your team by having certain stocked items. We all know capacitors are always going to be a stocked item. PSC motors should be a stocked item, and then relays should be a stocked item. Now, some of these videos we introduced simple contactors and 9380s. Today we're going to talk about the 9340. Now, there's a lot of terminals on the 9340 when we get into it, and those terminals aren't all being used. But if you stay tuned to our series of videos, we're always going to talk about those terminals in a practical application or unpractical application, just so you can better understand why would I use normally closed. If the job of the motor is to turn off when it's not getting the call to run, why would I need that normally closed? So we want to not just talk about one portion of any relay that we introduce to you and leave out those other terminals. So we get creative to help you better understand those relays. Eventually we're going to get into boards, and you'll see a close relationship with the relays and the boards. The only difference is boards are working all the time because they're their own load. That's why they require 24 volts to be present on them. They're calculating time. And the time we're talking about is the on delay and the off delay. And we'll introduce some relays that actually have that already built into it, like the thermal disk time delay relay. We'll introduce that in the video here soon. But as we continue to go down this timeline, we start losing these components. And so we want to make sure that you're well aware of what these components do, because it's very practical for you have to go back down that timeline backwards and reintroduce these components. Now, we don't expect you to have a board, a fan control board on your truck. If you did, that would also be helpful too. Maybe it's going to be a permanent fix in what your customer wants and what the manufacturer's intentions were. You can find that combination with the control board. Getting right into it, the 9340 relay, we have this image up here. It's blown up. You can see all these terminals. This is a good clear image. It talks about, 1, 2, 3, 4 different jobs that it can do. Just by looking at this, 1 and 4, those are pretty much your line inputs. And then 2, 3, 5, and 6 terminals would be your load outputs. Now, just to wire this motor, I'm going to show you how I can do this in different ways, but I only have one motor. I only have one speed up here. I don't have multiple speeds to really show you. So in this video, you saw how we took a blower motor and we wired a couple speeds up to it. That was to help you illustrate those different speeds that we don't have up here on this smart board. We're integrating low voltage components, hence the transformer, the terminal block here, which is all low voltage, and the thermostat, just to kind of help you understand your surroundings, where you're working at. We don't have heat strips up here. We don't have any W terminals, because our focus is getting the relay wired up and getting the motor to come on and finding out where line voltage is present at all times, when the relay is in the off mode and contact voltage here is not being applied to the load, but how there's still power. So we're going to go over, as we wire this up one leg at a time, where voltage would be read and how you can read across this relay. So I think it's going to be a very good video. Getting right into it, I'm going to go ahead and talk about our legs of power. As you can see here, L2 I've colored black, and if you look here at my motor windings, common run and start, my common winding is also black. That's just to help you identify that this leg of power will be applied to common. And if you notice, my run and my start windings are color-coded red, just like my line 1. So as you follow this in the wiring series, you're going to find that L1 is present on these two, L2 is present on the common. So I want to make sure that you all understand that when you're working on this, you're going to have, you're not going to have it so easy. You're going to be working probably above your head in a small work environment that's very dark. There's a lot of other components in there. There's a lot more wires in there, and it's going to be very difficult for you to see. So we want to make sure that you're extremely confident when you're wiring this up, because you're not going to have it so easy watching this video when you're out there in the real world trying to put this in. There's going to be a lot of things that are going to obstruct your view. There's going to be a lot of things that are going to be interrupting your level of patience. It could be their shop calling you to find out when you're going to be at your next appointment. It could be the customer asking you how much longer it's going to take. Meanwhile, you're trying to get them up and running the best you know how. So trying to do this as easy as possible. I always say start with the high voltage, then work your way down to the low voltage. This way you don't cross high voltage and low voltage and create more work and create an unsafe situation. Now, when we do our high voltage, we want to work on one leg and only one leg until that leg is completely wired up. Once that leg is completely wired up, it's good practice to then do the second leg. So what I mean by that is I'm not going to work on L2 and L1 at the same time. For example, we have a transformer. It needs both legs of power. So if I said I'm going to use, go and get my colors just right. If I said I was going to land my transformer like this and say, okay, that's done. Now let me go ahead and work on the second leg of power. Okay, that's not a good idea, because even though, yes, I just finished the one leg for you, there's still a possibility that I could accidentally, let me just erase that last step. I can accidentally come over to here and miswire something, and then the moment I come over and I start to land power on everything else, we could have a serious problem there. So what you want to do is don't work on one leg and go back to the other leg. Work on one leg all the way through, and then when you think that you're done with that leg, you really want to inspect that leg and verify that you have landed it on all the proper terminals, so you don't butt two legs of power together, which, even though you're not going to run L1 to L2, but the way we just drew that, we did. So you have to be very, very careful to go ahead and finish one leg, inspect it, and then make sure that leg is complete. So we're going to go ahead and do line voltage 2. Our transformer has nothing on it. We have line and load. Well, if you look at line, this is line, so line's going to go to line. All right, and so there's one leg of power on the transformer, and I'm going to finish up L2. Now, if you look at the 9340 earlier in the video, we talked about it when we're at the light bulb, how we can tell contact voltage from coil voltage. And so if you study that and you memorize that, then you'll remember that L1 is line. So I'm going to come over here. I said L1, I meant terminal 1, which is right here. That is line. So is 4. Now, just to bring this fan motor on, I only need to work on one pole. I don't have to work on this second pole. The only other thing that needs to take place is I need to come over here to my normally open terminal, which would be 3. Okay, that means 3 is not running unless I have 24 volts present at the bottom of my relay, and once that's present, then this contact that's normally open will close. And so once that closes, then 3 will make, and we'll have L2 supplying power on our common winding. So now I can step back, I can look at this and say, does L2 need to be anywhere else? Well, let's look at that. We checked that box, so we're just going to label this L2. We're going to label that L2. okay? I'm going to label this L2, and I'm going to label that L2, and that's it. I know my L2 is done. L2 doesn't need to be anywhere else, okay? And so now we're going to go ahead and wire up L1. We're going to come over, and we're going to first land it on the transformer. And at this point in time, the transformer now has 240 volts of power on it, so we'll have 24 volts on the load side of the transformer. However, we're not going to jump into the 24 volt side until we're completely finished with this second leg of power. So where else does L1 have to land? Well, the run winding has to have a second leg of power. So between here and here, we now have 2 legs. And our start winding needs to have it. Now our start winding is going to be able to get its polarity from this capacitor. So we can't just run L1 to this, because if we did that, that's not enough. We almost need to introduce what's called a third leg of power, even though it's technically not there, but we're not going to get polarity to run without a run capacitor. Let me go ahead and just delete that last step. And so what we'll do is we'll come over with L1, and we'll land it on one side of our run capacitor. We're going to go ahead and label this L1. And then we're going to come out of that run capacitor. All right, technically this is our now third leg of power. And now we have an independent leg on our start winding. And with this, even though it's still presently L1, we'll have polarity and that motor will turn on and run. So, of course, this is L1 here. Now, one of the things I've showed you on the other videos, I'm going to continue to keep that in mind. Where is power present right now? Because this relay does not have 24 volts on it. So am I really reading L2 here? And the answer is no. I'm not reading L2 there. So I'm going to back a few of these back down to no value so we can see what value is really there. All right, so if you look at the path of electricity, L1 comes through the run winding over to the common, and it sure does on the start winding too. So that means at this point in time, L1 is present all over the place. Now, if I took my meter and I wanted to see what I had between run and common at this moment in time, all right, presently I would read 0, but if I were to touch it, I would get electrocuted. Now, the reason why I'm reading 0 here is my meter is reading no difference because you can't read a difference between L1 and L1. It's the same leg. And if I went to ground on one lead and started to touch my other lead to any one of these other respective terminals, I'm going to read one leg of power. But if I come here, at this present time, I'm going to read 0. Not because there's near 0 volts. It's because it's the same leg. So if I'm L1 here, then if you trace it back, that means at this present time, on terminal 3 of the 9340 relay, I'm also L1 there at this present time. So if I wanted to see, why is my motor not running? I don't have any 24 volts on my relay. I could come up between terminal 1 and terminal 3, and I should read the difference between L1 and the difference between L2. We're going 2 different ways here. So if I went up here and I read 240 volts, and I read 240 volts here, then I'm also going to read 240 volts here, because I'm reading L1 and L2. And so I know my relay is not closed. Now, if I put my meter from here to here on terminal 2, even though I don't have anything wired up to it, I'm going to read 0 volts. But if I were to touch terminal 2, I will get electrocuted from the second leg. And so we demonstrated that earlier when we were at the light bulb, where power was present. So we always have to respect electricity. Just because you read 0 doesn't mean there's not voltage. There's only 2 voltages we can read in a 240 application when we're trying to find out if something is open or something is closed. If it is closed, you will read 0 volts. If it is open, you will read 2 legs. Here it's open, we're reading 2 legs. here it's closed or reading 0 because L2 is present here. So even if I went from here to here, I will still read 240. Understanding our path of electricity is very important. That's why these videos are very special for me to put out, so I can better help illustrate this on this very expensive technology that we have here. We're going to go ahead and leave L1 and L2 present right now until we apply 24 volts to this relay. So getting into it, I'm going to try to color code this the best that I can. We already have red up here. I'm going to go ahead and say that one's going to be blue for common. So we're going to say 24 volts comes over to our terminal block. And there's no fuse that I have here present. We'll get into other low voltage videos where we start integrating fuses and stuff. We're just trying to stay focused on getting this relay to run. Like I said before, if we integrated everything, we'll be here for 90,000 hours, which is great for the channel, and maybe we'll get there. But we can't get there in one video. Coming out of here, we're going to give the thermostat 24 volts. And then for us to have a display, if we're not using any kind of DC voltage like batteries provide, we're going to have to provide a path back to the transformer. And with this, I've created a loop or a path back to the transformer, and now I can have a display. The thermostat is going to take this 24 volts and it's going to relay it over to all the prospective terminals that has been designed to or programmed to put power on, whether it's in heat mode, cool mode, or just the fan in the on position. We're going to go ahead and say we need Y and orange next. So we're going to go ahead and do O. Okay, thermostat puts power out on O for a cooling call. It puts power out on Y for a heating call, but it also brings on the condenser. So if it's a heat pump, you won't have the O, you'll just have the Y. Not we're trying to explain that, but just throwing that out there, because if I didn't have O, Y is the condenser. If it's a heat pump, it's going to put out heat, and the fan needs to run with that. So Y and O, when we get into other standard air handlers as we progress on our timeline, we're going to talk about these two terminals and how that's important for multiple speeds on your motor, to have the ability to toggle between low, medium, and high speeds. Especially when we start talking about variable speeds, these terminals on this block are very important. The only one that we're concerned about in a very standard application like this would be just the G call that the thermostat provides. And as long as it's programmed correctly, you'll always get a G call in the event that it needs to run in heat or cooling, right? And so once we get this G call, this is what we want to wire our relay to. We want to wire, yes, the fan needs to run anytime you have the rest of these, but primarily the G call. Because what if you just want the fan to come on by itself? The fan's always going to run with the contactor, whether it's contactor only or contactor with reversing valve, right? If we had a W terminal and it was energized, the fan's always going to run with it. So we really want to hook our relay up to this terminal here, which is the G. G is not for ground, not in the air conditioning world. In the electrical world, yes, but not in HVAC. Everything is color coded for the next guy coming out there. That next individual needs to be able to recognize the patterns that are unique in our industry and that are very redundant. This way we can get through every call, every job very safely and efficiently. Now this relay is still not going to energize until I have a common. So we're going to go ahead and give it a common. So I'm going to come out of this bottom side. It doesn't matter which one of these you put 24 volts on, these bottom terminals here, as long as they're not on the same side. So we're going to come up and see how I want to do this. just like inside your air handler, wires are running all over the place, right? There we go. So we try to color code this stuff. And maybe that's why they also color code it inside your air handlers, so you know you better understand what's going on in that dark spot. All right, there's nothing else here to wire up on the low voltage side, but we need to change a couple of things. The moment we got 24 volts here, there's no longer L1 present here, and there's no longer L1 present here. The moment we put 24 volts here on this relay, we now have L2 present, okay? And because of that, L2 is now present here on our common terminal of our motor. And at that point in time, both legs are present. We have a capacitor in circuit, and this motor is going to run until we lose the G call. Once we lose the G call, that'll come back to L1 because it's open. This will come back over to L1, and the motor does not have two legs of power, so therefore it can't run. That's pretty much all we have to talk about on this here. These other terminals, you know, could I take L2 and put it here and here? Yeah, sure. We'll go ahead and do that real quick. Let's see what that looks like. We'll try to make this as clean as possible. I'm going to put green back over there. So I could put L2 right here, right? And that means L2 would be present here because I have 24 volts. Because 1, 2, and 3 is a pole all by itself, right? 1 to 2 is normally closed. 1 and 3 is normally open when I have 24 volts. 2 opens and 3 closes, but it's its own leg. So if I shifted L2 here between 4, 5, and 6, which is its own pole here, then what will happen is there's no difference. I can reserve this top pole for something else. If you look at the video earlier, we put a couple of light bulbs and different fan speeds on these just to help illustrate where power is present, when power is not present, what's happening. So this bottom piece down here, you have, I'm just going to mark them off in a non-confusing way. This is the same, and then this is the same. So this is not a pole. This is your coil voltage. So you have pole 1, which 2 and 3 switches are on that pole. You have pole 2, which is terminal 4, which 5 and 6 switches are on that pole. It's not good to ever put two different legs of power here. Like I wouldn't want to come and put L1 here and L2 here. Would it work? Yeah, but there's not a whole lot of plastic dividing this, and when you start getting your meters in there, if your leads are very long, they could touch, and that would very much hurt because that would be putting two legs of power together. We don't want to do that. I'm going to leave it off on this note so you can just see this last image here. But that's everything. I hope that this 9340 is less challenging. I hope you can look at this relay and say, sorry. I hope you can look at this relay and say, I want to stock this item. I'd like to use that somewhere. And if you think that because you're not using these other terminals that it's a waste of a relay, don't think that way. If that's all you have, please use it. If it's not, maybe you want to save it if you're doing something else later that day that you may think that you need it for. But it's a lot more expensive to make a second trip than it is to go ahead and take care of things while you're out there on the first trip. My opinion, you know, stocking this relay allows you to do more in one visit, and that's a bigger savings than you know, the difference in cost between this and another relay. All right, we appreciate your support by subscribing. Liking our videos is very important. It helps support the algorithm. Please, you know, many people in the industry that, either like to know this stuff or they're challenged with this stuff, take the time to share these videos with those other technicians or people that are learning. This is a great industry, and it's our job to share knowledge. That's what I'm doing here. There's a share button that you can just simply share this to all your friends, co-workers. Maybe somebody wants to know a little bit more than they know now, and maybe you think that they don't need it, but I'm hoping that every video that we release, there's something new that can be learned. Stay tuned. We appreciate your support.